So hello, today we would like to introduce our project, the Atlas of Mars from Emirates Mars Mission Observations, which will be presented by Shamshir and me, Katerina, as a part of Mars Research Group at the Center for Space Science in New York University in Abu Dhabi.
The Emirates Mars mission, or the EMM probe, was launched in July 2020 from Japan. EMM is the United Arab Emirates' first mission to Mars and Arab world's first mission to another planet. Due to its unique orbit, the HOPE probe provides global images of Mars while preserving details about major geological features, albedos, variations of polar ice caps, dusts, and cloud cover. In this project, we aim to create a two-dimensional color atlas of Mars by combining red, green, and blue filter images taken by Emirates Exploration Imager, or EXI. The map can serve a scientific community in UAE and the world in visualizing scientific data such as magnetic anomalies, mineralogical composition, and thermal data on an accurate and high-definition map. Additionally, it will be used to engage public in geologic state of red planet. Let's have a look at its scientific instruments.
There is the Emirates Exploration Imager, which is a multi-wavelength radiation-tolerant framing camera. This camera consists of two separate ultraviolet and visible telescopes. The ultraviolet telescope enables measurements of ozone and ice clouds in the Martian lower atmosphere, and the visible telescope captures high resolution, specifically 12 megapixels color images of Mars. The Emirates Mars infrared spectrometer is a spectrometer designed to operate in the infrared band, and it balances the coverage and performance requirements, allowing highly accurate temperature measurements. It provides the linkages from the lower to the upper atmosphere in conjunction with MUS and EXI observations. And the last instrument, the MUS, Emirates Mars Ultraviolet Spectrometer, is an imaging far ultraviolet spectrograph that measures the variability of the Martian upper atmosphere, and it determines the abundance and variability of carbon monoxide and oxygen in the thermosphere, and calculates the 3D structure and the variability of oxygen and hydrogen in the exosphere.
So the EXI data was acquired in Flexible Image Transport System, or FITS format, and was pre-processed for further analysis. We utilized EXI images that are at a high enough altitude to show full disk of Mars. Those images were then manually sorted into three categories, where the disk was fully visible, half visible, or more than half of disk is visible. We follow by discarding the category 3 images where less than half disk was visible, and we proceed by extracting the latitude and longitude pixel reading value for first and second categories at zero height. To generate a global map of Mars, we begin by transforming the data from EXI images to a planar 180 cross 360 degree map. This is performed by utilizing the latitude and longitude coordinates assigned to each of the F635, F546, and F437, that is the red, green, and blue channels respectively. We ensure those pixels are at zero height to ensure the presence in the planet's disk and not in dark space. Constraints were applied on the pixel values for different image categories to discard any overexport or poorly lit features. So the first method we used to make a 2D map was Robinson projection. We converted our longitude and latitude coordinates into the Robinson projection using equations displayed on the screen. Here R is the radius of Mars at map scale. X and Y are the Robinson projection indexes. Lambda is the longitude in radians, and lambda naught is map center median in radians. Upon obtaining X and Y pixel values, we begin generating the map by assigning each coordinate with its corresponding value. In the case where two readings have same coordinates, they are added together and simultaneously an index map is made that records the number of pixels contributing to each coordinate. Upon completion of the map, each coordinate value is then divided by the corresponding index value of the number of contributing pixels to find an average. This methodology works when we have enough pictures of Mars to have multiple readings of the same geographic location at different altitudes and viewing angles to allow us for an accurate average representation. It is expected that with more images, the map quality and the cohesiveness of pixel will improve.
We also created the cylindrical projection map, and there are some variation observed in the altitude and the solar zenith angle in terms of brightness and feature definition, making it evident where data from one image ends and the other begins. And we use two methods to correct for these variations. First is the machine learning, and we calculated the percentage overlap between two images covering the same geographic location. Using this overlap region, we trained the network to generate a corrected model that can predict the corrected pixel values of an image. And then we also used the fine pixel stitching, and we divided the map into sets of 2 × 2 pixel squares, where all 4 pixels are from the same image, and pixels from neighboring square sets are compared to determine a multiplying factor to adjust the brightness of square 2 to match the that of square 1 without losing fine details. Also, Martian disk isn't always fully visible due to the position of the planet with respect to sun. So we added another processing step to only utilize pixel values that are within the solar zenith angle range of 23 to 55 degrees. And this range was determined based on observations made on a sample of 20 images to diminish the presence of dark and overexposed pixels. Here you can see our findings and results. We created several disks of Mars, and we labeled them to be more accessible to the public. And on the next slide, you can see the global map of the Robinson projection, and this is created from 582 images which were taken between February 10th and August 30th, and they were combined to create this map. And the same was also for the other map in the cylindrical projection, as we have on the other slide. And these are our results. And here you can see the labeled global map with the most important features highlighted.
So our project successfully completed its primary objectives, and fine pixel stitching method yielded accurate results and produced a map similar to the ones currently available publicly. And the project advanced to collect and plot the UV day glow emissions from the EMMS and Martian surface temperature data from EMMs. Those are the two instruments aboard the EMM probe. The salient features displayed on our map, like craters, poles, dichotomy, quadrangles, and different planetary coordinate systems, were labeled in our atlas. So in future work with the given number of images in batch 1 of EMM data, we were able to obtain latitudes between -19 to 53 degrees and generate a map with resolution of 900 × 1800 pixels. Upon the release of new EMM data, we plan to expand upon our global coverage of the map and hopefully cover all latitudes, in addition to increasing the map's resolution up to at least 2340 × 4680 pixels, making it the most detailed map of Mars ever produced. Additionally, we aim to fully utilize machine learning methods since it is highly effective. However, through implementation, we noticed the training prediction ratio of 4 is sufficient to yield accurate prediction. Upon completion of this map, the team will focusing on designing a detailed atlas that will highlight the all key geologic features like they are present in the current public versions of atlases and all the 3D softwares available online. And we also plan to make an open source software for UAE community and science enthusiasts, like the JMARS made by NASA and Arizona State University. We also plotted the data from EMUS and EMIRS instruments that is currently visible on the screen, and a current open source version of our atlas is also available on the screen. We would like to expand all of these works further and make them available to the public. We all thank you for being a part of our presentation.